The aim of this series of presentations is to provide you with a solid foundation in microcontroller programming and the techniques for interfacing microcontroller with sensors. The contents of this presentation will be based on the book I authored, C Programming for the ATMEGA 328 microcontroller. My goal is to share the insights and expertise I've developed while authoring this book. The agenda for today's presentation. My presentation is structured into two segments. First segment, I'll explore the various processing units, highlight their capability and typical applications. The aim of this segment is to provide you with a general understanding of the diverse range of processors available so you can get an idea of the niche occupied by the microcontroller. This foundational knowledge will assist you in determining whether the microcontroller is the optimal choice for your design. The second segment, I'll shift focus to discuss microcontroller characteristics with particular emphasis on the 328p microcontroller. I'm going to be presenting 6 types of processing units. Each type offers unique features and capabilities that cater to different industries and domains. These are the microprocessor, GPU, PLD, FPGAs, ASICs, and finally microcontroller. So first let's start with the microprocessor. The microprocessor performs all arithmetic, logic, and control functions in your computer. It's the CPU that you have in your laptop, basically. To make it work, you generally need to integrate the following hardware components. So you buy the microprocessor, but in addition, you have to buy the following components to make it work. You need to buy memory, random access, and read-only. You need to buy clock generators, power supplies, input-output devices, supporting chips, and cooling systems. And then you need to integrate all these components in what's called a motherboard. So buying the microprocessor by itself is not going to allow you to start programming, but you have to buy a number of components which you need to have the knowledge to be able to integrate them. Typical example of microprocessors are the Intel Core series and the AMD Ryzen series. Next, I'm going to be talking about graphic processing units, GPUs. GPUs excel when your application requires parallel processing, such as graphic rendering, scientific simulation, machine learning, or artificial intelligence. For you to get an idea what the GPU looks like, I'm going to compare it to a microprocessor. So a high-end microprocessor CPU may have between 4 and 16 cores. That means it can run up to 16 parallel process. On the other hand, a high-end GPU can have thousands of cores. This means that for tasks that can be effectively parallelized, such as graphic rendering or deep learning training, it should be handled by GPUs. Typical GPUs, you have a Titan 5 NVIDIA or NVIDIA Tesla V100. Now, to give you an idea of cost, a high-end microprocessor may run, let's say, $700–800. A high-end GPU runs $20,000 to $30,000. Now let's have a little GPU a sample GPU utilization for artificial intelligence. I'll start with a definition. A neural network are algorithms designed to recognize patterns. They interpret sensory data. So, for example, if we have an image recognition learning process, first the sensory data would acquire the pixels from the image. You have a camera that looks at the picture and acquires the pixels. Then you would have the neural network designed for image recognition, would take these pixel values as input and learn to recognize patterns that distinguish one image from another. So let's assume you have a self-driving car. So the first step would be to teach the system what the cars look like. So and what the traffic look like, and all the look at what the environment is going to look like as it drives. So that's on the learning phase. Well, then once it's learned, then you take it out, and the artificial intelligence camera is going to be looking through the right, left, and front and back of the car, and it's going to decipher what's out there based on what's learned. And then you will be able to get from point A to point B. Now, when the camera is looking at the different objects, other cars, people, whatnot, all those things have to be looked at in parallel, so you can decide whether it's safe to continue or needs to stop. So anyhow, that I think that gives you a idea of what GPUs do, what they are used for, parallel programming, and hopefully I haven't confused you too much. So let's go to the next item, which is ASIC, Application Specific Integrated Circuit. These are designed designed and optimized for specific applications. They have a lack of flexibility in the sense that once you build these ASICs, there is no way to modify them. It is what it is, and if you don't like it, then you have to replace it with a new ASIC. Now, it is expensive to develop, and it takes a lot of time. However, it may be justified if you have high volumes, need for high volumes of this chip. An ASIC development cycle, they are typically they range between several months to years, depending on the complexity. So basically, you have a reason to make your own chip, and because of performance or high volumes, and it's something that is made for you, and you don't get to modify it, but you need to replace it if it eventually doesn't meet your what you need. Let's talk now about programmable logic devices and field programmable gate arrays. These are programmable chips that you buy, and then you can burn in the logic. To implement a design using PLDs and FPGAs, you typically need to characterize your system in terms of logic behavior. You need to describe the interconnections of your digital circuit, and then you have to use the hardware description language such as Verilog or VHDL to burn in the logic into the chip. So this is something that is done by people with specific training, and usually like electrical engineers that know and specialize on digital algebra and this type of things. It's not done by programmers, let's say. FPGA development cycle, usually they run typically a few weeks to several months. Now below I have a table that is going to give you an idea of the difference between PLDs and FPGAs. PLD, when it comes to complexity, PLDs are moderately complex, while FPGAs they have complex designs, and the difference is the number of gates that come on a PLD or an FPGA. FPGA has many more gates than a PLD. So you can program more things, and you can have more complex designs. The PLD reconfigurations, once you build you burn your logic into a PLD, you're really not thinking about you're going to have to reprogram it. On the other hand, with the FPGAs, once you program your logic, there are so many gates that you'll have the capability to add to the logic or remove some stuff and add others. That's due to the number of gates. Performance, the FPGAs have a better performance than the PLD. For production, volume production, you usually FPGAs would be much higher volume than PLDs. So we finally got to the microcontroller. A microcontroller is a self-contained computing device that integrates processor, memory, and input and output peripherals on a chip. So you have a chip that it would be equivalent when we talked about microprocessor. A microprocessor, you needed a motherboard, you needed to add memory and all these components. Well, a microcontroller is a chip that has already incorporated all those components. So it's like having your little mini computer at the cost of $20. For example, the microcontroller include timers, analog to digital converters, digital input-output pins, communication. Has many communication interfaces such as UART, SPI, and I2C. It also has pulse width modulation, signals that you can put out. The microcontrollers are commonly programmed using C or C++ or assembly language. So if you're a programmer, you can actually do something with these chips. You can write a program and load the program and make it do something. Connect this chip to a sensor and do something for $20. Next, the microcontroller integrate development environments IDE like the ATMEGA Studio streamline the process of developing, outloading, and debugging the C and C++ program. So once you buy your microcontroller, there is a number of IDEs that you can use where you write your C programs and then you debug those C programs, then you load it into your into microcontroller, and then you can do something. Applications frequently employing microcontroller include Internet of Things, robotics, and drones. For example, on the Internet of Things, microcontrollers control connectivity and control in smart devices. When it comes to robotic system, microcontrollers control movement, sensing, and decision making. For drones, microcontrollers communicate with flight control, navigation, and performs data processing. Now, how does it do that? The microcontroller communicates, for example, with the GPS module, inertial measurement unit, and wireless transceivers using the UART, SPI, and I2C. These three are three serial interfaces which are mainstream in the industry. Microcontroller communicate with motion sensors, light sensors, again via these serial interfaces, UART, SPI, and I2C. Most of the sensors that you'll find out there, if not all, they all communicate in one of these three serial interfaces. Next, the microcontroller can control actuators using pulse width modulation, allowing precise control of motor speeds and servo positions. So this concludes my first presentation. My goal here was to show you the universe of microprocessors, so you can see the niche occupied by the microcontroller. Because it's hard to start just with a microcontroller if you really don't know what's out there. So this gives you a universal view, and the next time we're going to dive into microcontroller. But then you'll have a good understanding why is it that you need the microcontroller. So anyhow, I hope you've enjoyed this, and thank you very much.